Okay. Then you suppose you have some event queue. Okay. So in a system you can have multiple queues. Okay, and each and every queue is keeping track of different processes which are in different states. If a process is in IO state, then we have a IO queue. If a process is ready to run, then we have a ready to run queue. Then there is actually who is doing this? Who is taking from disk a program and loading into memory? Now here comes different types of schedulers. Actually, long-term scheduler is responsible for taking program from disk and bringing it to ready to run queue. So generally, long-term scheduler is responsible for increasing the degree of multi-programming. If there are more number of processes loaded into the memory, then the degree of multi-programming will be more. If the degree of multi-programming is more, then the CPU utilization will be more. If the CPU utilization is more, then throughput of the system is also more. Throughput of the system means the number of jobs that can be processed by a system in a unit time is called throughput. Okay, so this throughput will have impact. So depending upon the degree of multi-programming, the effective utilization of the resources and the system performance and throughput is dependent. But to a certain level, now let's talk about this, the number of processes and this degree of multi-programming. Okay, this is called performance of a system. We call it as degree of multi-programming. If I move from here to here, it means I'm increasing the degree of multi-programming. If I move from bottom to top, it means throughput is increased. Throughput. So if I go on increasing the degree of multi-programming, throughput also increases. But at certain level, what happens if I go on increasing the degree of multi-programming, the throughput will come down. Okay, this state is called thrashing. So we should not allow so many number of a process to be accommodated into memory, so always the CPU is busy in performing preemptions, performing in context switching. So that kind of situation is called thrashing. So we should avoid this kind of scenario. So all this controlling of degree programming will be done by a scheduler called long-term scheduler. Long-term scheduler. Okay. Now, then when long-term scheduler takes a program and loads it into the disk, and it's ready to run queue, then all the process they are waiting for their turn to be executed on CPU. Then there is one more scheduler called short-term scheduler, which is responsible to take a job or a process from a ready queue and give it to the CPU. Then this short-term scheduler is also called as dispatcher. Now what is the difference between scheduler and dispatcher actually? Here scheduler is nothing but which takes a decision. Okay, it's a master. But whereas dispatcher is a slave which obeys the decision, which the actual work will be performed by the taking of process, this context switching task will be performed by dispatcher, but the decision of taking that process is taken by the scheduler. So scheduler takes decision and decision will be carried out by the dispatcher, which is your short-term scheduler. And there is one more called middle-term scheduler, which when a process completes its execution or it has performed some IO operation, it has to be taken and has to be kept into this queue. Okay. Now this is the job of middle-term scheduler. So middle-term scheduler responsibility is to keep this in specific queues, okay, while it is running. But whereas the degree of long-term scheduler is to increase the degree of multi-programming or to control the degree of multi-programming. Now here we talked much about preemption and context switching. So let's I would like to spend 2-3 minutes on that. What do you mean by this context switching and what do you mean by preemption? And then we'll start these algorithms. You have a CPU and process PA is executing on this processor. Then while executing, it has not completed its execution. If I am forcefully taking this if I am forcefully taking the CPU from this process, then it is called preemption. Okay, while doing preemption, when next time I give this process to the CPU, then the CPU has to start execution from the point where it has left earlier. For example, if my program has 100 lines of code and I have executed 25 lines, and here preemption happens. Okay, if here now preemption can happen at any point of time. So if this preemption happens, then another process will be scheduled. When it turn comes again, then this process has to start execute from the point where it has left earlier. It should not again execute right from the beginning. Okay. So how it is possible? It is possible, as I have told you in the very first lecture, that operating system act as a it controls the flow of execution. How does it controls the flow of execution? It controls the flow of execution by program counter and instruction register. Program counter always point to the next instruction to be executed, and instruction register contains instruction itself, right? So when this instruction is executed, then program counter will be incremented and it points to the next instruction. So like the sequential execution of a program happens. So whenever here preemption, whenever here context switches, whenever I want CPU to snatch from this process, what this process will do is, before it is preempted, the short-term scheduler, what does is, it will save the context of a CPU. What do you mean by context of a CPU? All the memory contents, all the register contents of a processor will be saved, and it will be kept in the process control block. So when the next time this process is given chance, then from the process control block where the attributes are stored where the attributes of a process are stored, okay, that will be retrieved back, and the context of a process will be reloaded again. And again the execution will resume from the point where it has left earlier. So process control block plays here a very important role, and which actually store the context of a CPU, right? So context of a CPU is stored in process control block, and context is nothing but the contents of CPU registers. Okay? So this is called context switching. It means when a CPU want to execute another process, okay, it has to save the contents of present process, contents of register which are filled by one process, which are actually with regard to one process. And if the CPU want to execute some other process, then it has to flush all those and load this register with the new process context. Okay, so this switching of context is called process switching. Okay, all the contents of the CPU register will be switched from one process to for one process to another process. The contents of the CPU registers will be flushed and reloaded again. This is called context switching.